Alright, we're going to start to get into more complex problems. So far, I hope that you have been thinking this hasn't been so bad as you've been doing some of these problems. All we've been doing is finding the minimums and maximums of a function by deriving. What you will find as you get into these higher number problems is that they are going to be a little bit more complex. The functions that you have to create are a little bit more complex, and overall then the driving is just a little bit more complex. So we're going to work through 41, and what I have gone ahead and done is drawn the picture for the problem that we have at hand. So there was my step 1. Alright, the other thing that I'm going to bring into play is I do know that this has to be 3,000 cubic feet. Okay, that's given right here. They gave us a certain volume, and we also know the cost is going to be based on the overall surface area of this tank. So we are going to be trying to minimize the surface area. When I did this problem, it took me a little bit to figure out what I needed to do. What I decided to do was just look at the cost per unit. So I'm just going to say that cost is $1, let's say, for every square feet. So by going off the fact that cost, which we could call, I'm going to just call it K is my cost, okay, for a unit, and I'm just going to say it's $1. I'm going to just pretend it's $1 for now. Okay, so really all I want to figure out is what is my smallest surface area that I can come across in this scenario that's going to get me therefore the most minimized cost. So I'm going to look at, as my primary, what I'm overall going to be trying to minimize is the surface area. We are going to have to be looking at a few things here. So I have a sphere. I'm going to bring this out actually for now. And what I'm going to go ahead and do is I'm going to give the formulas that we might be interested in. So for a sphere, the volume of a sphere is going to be given by that equation, and the surface area of a sphere is going to be given by that equation. I found these in the front of your textbook. And a cylinder, the right cylinder, is going to have a volume equation of this, and then a surface area equation of this. So by the way, this thing is the tank that our problem was asking for. So I mean, there's the top of our tank, the bottom of our tank. What they said was we have a cylinder with two hemisphere or half sphere ends. So there's what we have. Overall, what we have then is we're going to be looking at the surface area of a complete sphere and then the surface area of a cylinder tank. So I am going to pick now the surface area equations, because like I said, I'm going to need to have the surface area of one full sphere calculated. So I'm going to go ahead and put that there. So there's the surface area of my sphere, but then plus the surface area of our cylinder. So one thing that we are going to have to take into account though is the value of the surface area of the cylinder is actually 2 times the value of our cylinder. That was given in our problem. So what I am going to do is multiply the surface area of our sphere by 2 because it's worth 2 times as much as that of the cylinder. So I'm going to go ahead and just write that in here. I'm going to take this times 2. So I'll rewrite this. What we have is the surface area is equal to 8. I would like you to notice that our surface area is written depending on 2 variables. Basically, the radius of this whole cylinder, which is going to in turn affect the radius of these spheres, and then the height of this cylinder. So I mean, based off of those 2 things, that's where our surface area is going to come into play. But remember, if I were to try to derive this right now so that I could find the critical values and therefore the minimum and maximum points, I would have issues because which variable am I going to derive it in terms of, r or h? So we want to get it in terms of 1. So I am going to need a secondary equation. And in that problem, you would have noticed that they gave us volume. So, I mean, right off the bat, you can kind of see, yeah, I'll probably be having to use volume in here somewhere. So I'm going to go ahead and do our volume equation now. And volume is going to be equal to, well, the volume of our sphere, and then plus the volume of our cylinder. The other thing is we actually do know the volume because it was given to us. So it's 3,000 equals 4/3 pi. I'm going to just solve for my h. I'm going to get h in terms of r. So I'm going to isolate h because that way when we go back up to our equation up here, I can plug in for my h a function in terms of r, and then that way we would have gotten our surface area all in one variable. So the first thing I'm going to do is, this is all a chunk, so I'm going to get rid of this chunk by literally subtracting it off. Here I'm just going to be taking this factor, this whole factor, or this whole grouping, and dividing it from both sides so I get h by itself. So in the end I'm going to get, okay, so what I am going to take is this equation right here and this equation right here, and I'm going to sub in for my h this crazy equation. Okay, so here I go. I'm going to move this down. So surface area is going to be given by 8. Okay, and I am going to simplify this. These cancel each other out. One of these also will cancel it out, so I'm just left with 1r and then 1 up here. This is all going to simplify to b. I'm going to take this 2 and distribute it to everything. Alright, so here is my equation. This was a lot of work, but that was all just step 2. I have now completed step 2. So now that we have our actual primary equation, I'm going to just focus on that. What we are going to have to do is consider a feasible domain. So r is our input, and once again, radius, I mean, it has to be something from 0 to infinity. Okay, so make sure that we have a positive number in there. And so now finally I am going to go ahead and derive all of this. So I'm going to find the surface area derived. So what I'm going to find is that this is a constant right here. I'm going to get 8 pi and then times 2r plus, and then here I am going to have to go ahead. I'm deriving term by term. I've already derived this term. Now I'm going to have to derive this term. So plus, and then I will have to do low d high. So low. Alright, so I am going to simplify this all out. S prime of 16 pi. I hope you'll notice that these are going to cancel each other out here. So I'm just going to get r times all of this. So we're going to get negative 8 pi times r cubed. Combine these terms to get minus 6,000 over r squared. I am going to go ahead then and get a common denominator so I can combine all this. So if I do multiply this by r squared, I have to multiply the top by r squared. What I'm going to get is s prime now of 16 pi r cubed plus negative. So what I've gotten after all of this is this equation right here. And what I want you to realize is that technically all of this is going to be multiplied by some kind of payment k. Alright, we'll call it, let's say we charge $20 $20 times all of this number of surface area. But the idea is that's some sort of constant. So when I go ahead and set this equal to 0, alright, equal to 0, I do have some sort of cost that I'm charging for all of this, but let's see, let me write it. That k would cancel out. So, I mean, I would divide both sides by k, but it's going to be lost to this 0 over here. There's a couple of ways you can do that. There's a couple of ways you can do this. You can actually now take this function, figure out when it's equal to 0 by graphing it on your calculator. That always is an option. I'm going to allow calculators on these, especially for these application problems, because I mean they take a lot of math. I'm also going to say you could solve this by just setting that top equal to 0, so we get 32 thirds. So I am going to solve for this. I'm going to multiply it by 3 over 32 pi. And because that would cancel these out and cancel these out. So what I get over here is times 3 over 32 pi. And anything that we can cancel out here, I'm going to say I can cancel out a 2 in all of this. Actually, what I do get when I reduce this in my calculator, I get 375 over 2. So when you multiply this all out, what we're going to get is 1,125 all over 2 pi, and then I'm going to cube root all this. And what I get is R is approximately 5.636. Once again, if you would have just graphed this on your calculator and found your zeros, you would have gotten the same thing approximately. And then so now what you can go ahead and do, and this is way, way back up here, I'm going to scroll up. This equation right here, I can now use, so I'm going to take down and I can now plug in this 5.636 into this whole entire equation for my R's, and what you will get for H when you do that is approximately 22.545 feet. So once again, revisiting what we did was this radius of a tank and this height of a tank. Those right there are what's going to get us the most, a 3,000 cubic foot volume tank, and then also it's going to be the smallest surface area possible with this situation that would make our cost the smallest.